This week I'll be describing a program I wrote in Power Basic to solve a connection optimization problem. The idea is to connect a given number of points located randomly to a central gathering point while optimizing the combination of two different parameters. The first parameter is total line length and the second is total flow length. Total flow length is the sum of the travel distance from each well to the gathering point. The total line length can be minimized with a Steiner Tree algorithm. However, this will give excessive flow lengths with often unacceptable pressure or signal loss at the gathering point. This problem has multiple applications. For instance, a gas well gathering system connects multiple wells to a central transportation, compression, or processing point. The reverse problem of single point liquid distribution is also solved by this program. Large residential grass lawns or parks may have a large network of sprinkler heads that must be supplied with water. In either of these cases, the idea is to have a low total length of trenched linear feet and at the same time have a low total flow length. This program will give multiple different designs. This allows for a choice of varied layouts to allow for varied boundary, terrain, or other constraints. I have not done a thorough literature search on this problem, so what I'll be describing is of my own design, although similar procedures may have been done before by others. You can watch this program run while I describe it. The program works by stepping out in small increments, starting from the gathering point where all wells must connect. Each step is either a single step or two steps radiating out from the same point. When two steps are taken, a single line then branches out into two lines. Calculations are made of both scenarios before that decision is made. At each step, all non-connected wells are assigned to the closest endpoint of any of the lines. So the endpoint on each line usually has multiple wells assigned to it. In other words, the wells are broken into groups and assigned to the closest line at its endpoint. Next, the single-step scenario is analyzed by computing the combined group assigned well distances from a potential step. Many potential steps are considered by varying the angle of a step. Note that each step distance is always constant. So total line distance between the line endpoint and all the wells in that group is calculated for each of the many angles. The angle giving minimum combined distance is saved. Next, a similar calculation is performed, but using two steps from the same endpoint rather than one step. Each well in the group will be assigned to the closest of these two steps. Again, each of these two steps is analyzed using multiple angles for each of the two steps. The combination of the two angles of the two steps that gives the shortest combined line distance is saved. Then, the single-step scenario is compared to the two-step scenario by comparing their combined line distances. If the single-step combined line distance minus the two-step combined line distance is more than the step length, then the two-step scenario is chosen and the line bifurcates or splits into two lines at this step. Otherwise, the single-step scenario is chosen. Then the process is repeated, starting reassigning all non-connected wells to the closest line endpoint. Then a line endpoint is chosen at random, and the procedure above repeated. As the lines are built out, you may see some small mid-course corrections due to another line becoming closer to a well than the line in consideration. When that happens, the well is assigned to another group, resulting in a small angle change for the line in consideration. This means that the program is constantly searching for the shortest combined line lengths at each step and is constantly adjusting as necessary. Here's a group of 6 different outputs from the same group of wells. Notice the differences between them. Also note the total line length I have written down in the lower middle for each of the 6 scenarios. The randomness built into the program allows for a variation each time you make a run with the same data. Here's a closer look at that group of 6 outputs. This one had a combined line length of 622. This one, a combined line length of 627. This one, 634. This one, 616. This one, 638. And this one, 621. Well, that's all for this week. We'll see you later.